It is professor at the University of L'Aquila.
1 year.
His research field is space weather, and in particular the interaction between solar wind, magnetospheric current with magnetospheric magnetosphere and ionosphere, and in particular with the production of magnetospheric currents. It is the leader of Italian PI of the data analysis of the satellite CSES, and that is between the collaboration of Limadusi and CS. And I'm happy to let the floor to Mirko, that will speak about the currents that have been created after was caused by the very bright GRB in 2021 too.
Thank you very much. First of all, I want to thank you for inviting me to have this talk. Today I will talk about the evidence of the upper ionospheric electric field perturbation that occurred in conjunction with the brightest gamma ray burst ever recorded. And okay, sorry. Please. Oh, okay. This story started a long time ago in a galaxy far, far away, and basically the observation of the probable emitter of the gamma ray burst that we will talk about, that occurred on 9 October 2022, and this is a little spoiler. It is the light curve that Integral measured during the gamma ray burst. It was called the bolt, that is the brightest of all time. It occurs around 2 billion kilometers away from the Earth, and as I will show you in a couple of minutes, it is the first gamma ray burst that caused a strong perturbation in the upper part of the Earth atmosphere. Here you will see the two instruments of Integral, but I will come back to this figure later. First of all, I will give you some introduction of what is a gamma ray burst and what is a ionosphere and so on. We'll start with gamma ray burst. They are short-lived bursts of gamma ray photons that last from a few milliseconds up to several minutes. In general, they shine hundreds of times brighter than a typical supernova. Non c'è audio? Però a me mi risulta. Sì, sì. No, a me mi risulta aperto. Can you hear me?
Yes.
Yeah, okay. Okay. And briefly, they are the brightest source of cosmic gamma ray photons in the observable universe. In general, the principal source of gamma ray bursts would be neutron star with neutron star, in terms of collapse of binary neutron stars, neutron star with a black hole, and the epilogue of a massive star. This is the in general the population of gamma ray bursts can be divided into two types. The first one is short burst in terms of duration, and the other one is long burst. And in general, the short burst and long burst have a different hardness in terms of spectrum. In fact, the short one has another harder spectrum with respect to the long one that are characterized by a soft spectrum. And it is only a philosophical point I want to tell you, that some studies show that gamma ray bursts might have may be responsible from mass extinction, and there are still people that told me that viruses are useless. But anyway, you can see here. And I will go further. I will talk about what is the ionosphere. The ionosphere is the upper part of our atmosphere, and this is the typical behavior in terms of altitude and electron density of the ionosphere. The ionosphere is, with respect to the neutral atmosphere, it is constituted by plasma, that is a gas in general, that is constituted by protons and ions and electrons. And you can see here the electron density from about 60 kilometers up to 800 kilometers. You can see that there is two maxima. The first one is what is called the E layer, and the second one is the F layer. Then, as you can see, start to decrease up to what is called the magnetosphere, that is out the outer of our ionosphere. In general, of course, as you know, since our atmosphere is constituted by general oxygen and nitrogen, you can have here the typical population of ions in the ionosphere with respect to, of course, of the altitude. And here is the concentration. And you can see here that in general, you can see that in the lower part of the ionosphere, you have a very bad concentration of oxygen, nitrogen oxygen, ion of oxygen, and ions of nitrogen. And only in the upper part that only the ion of oxygen plus and H plus and X plus. The ionosphere is directly connected to the magnetosphere because we think that the ionosphere is the principle of the direct source of what is called the plasma sphere, that is a region in the magnetosphere that is constituted by plasma. And at low latitude, closed magnetic field lines reach out to several radii, forming flux tubes, and this region is referred to plasma sphere. And you can see here that is directly connected to the ionosphere. What is the external source of the ionosphere, or why the ionosphere is formed? In general, the principal source of the ionosphere is also, of course, our star, that is the sun, that through solar ultraviolet emissions give rise to a stronger ionization of the upper part of the atmosphere, giving rise to the ionosphere. But there are many other sources, as you can see here, especially for the E region or the lower part of the D region and the F1 region, that give rise to a variation of the dynamics of the population of the ions in the ionosphere. I will show you here an equation. It's a very simple equation, but it is crucial in our manuscript, in our research. That is the continuity equation. It is a very simple equation that we told you that on the left side you have the dynamic of the density of the plasma density with respect to time, and that is directly connected with the production given by, for example, the ultraviolet emission by the sun, the loss rate that is given to the fact that you are producing ions and electrons, and there is a recombination between them forming neutral atoms, and the mechanism of transport. In general, in the lower part, the transport is mostly unimportant, and in F2 region, transport methods Q and are no longer dominant in the optical. From a chemical point of view, you have the typical photonization, you have the typical reaction, and especially the recombination. And here, for example, you have the O, the oxygen, in which you have, for example, photons that are from the sun, and give rise to, of course, to O plus and electrons. And this is the key reaction. And this is the key recombination on the ionosphere. Like starting from, for example, the O2 plus an electron give rise to 2 atoms of oxygen and, of course, an emission. What are the satellites that are, what are the key satellites in our research? The key satellites are Integral and CSCS. We use Integral for the characterization of the light curve of the gamma ray part. And we use the electric field detector in CSCS that you can see here, the 4 booms of the electric field that measure the electric field to have the measurement of the electric field associated, potential measurement of the electric field associated with the gamma ray part. There are 2 different satellites, not only in terms of size of the satellites. Of course, Integral is very big, is a real satellite, it's a very big satellite, while CSCS is mostly related to what is called to CubeSat or something like that. It's very small satellite in terms of platform. The first one, Integral, has an high elliptical orbit, and the apogee is at about 60,000 kilometers, while you can see CSTS has some synchronous orbit, circular, with a period of 1.2 hours, and orbits at very low altitude, that is 500 kilometers. What it means is this satellite is almost in the magnetosphere, and this satellite is in the ionosphere. So I come back to what I showed you before. This is the light curve of the 2 instruments that are on both Integral, that measure the variation of the photon flux with respect to the time. In red we have the speed instrument, while in black we have the IBIS instrument, and you can see that from 30 and 60 down to about 40 UTC, we have a strong variation of the light measured by Integral, and is a multi-peak structure with an intense precursor here at about 30 and 70, and a very strong emission that peaks at about 30 and 21, and it have a very long duration, and you can see here that we have a very soft gamma after too low detected by both instruments. In the energy range that are from 75 to 1000 EV for the speed, that is the red one, and from 0.25 down up to 2.6 MeV from IBIS. The fluence of the proton emission, as you can see here, lasts about 80 seconds, very long. The fluence was very strong, especially in the lower part of the energy range, and the energy emitted during the prompt gamma ray burst was about, as you can see here, 8 or 10 at 53 hertz, very high. Okay. Where was orbiting CSCS during the emission of the gamma ray burst? Here you have the planisphere The blue one is the CSCS orbit. The green one is the portion of the orbit that corresponds to the part in which the gamma ray path was observed by integral, and the gray area is the illumination area of the gamma ray burst. And you can see here that we were lucky because during the arrival of the gamma ray burst, CSCS orbits exactly in the zone that is completely illuminated by the gamma ray. The other fortunate event here is that the portion of the orbit in which CSCS could measure something potentially related to the gamma ray burst is completely outside of the principal ionospheric zone in which there are currents that are flowing. In general, I don't tell you this before, there are two zones in the Earth in which there are very strong currents that in general produce strong variation in the electric field. The first one is what is called auroral zone, which have very strong currents called auroral electric. And the other one is the equatorial zone, in which there is the equatorial electric. As you can see here, we are in a very lucky zone in which in general there are no currents that is flowing. So if we could observe something, here is the best zone in which we can observe. Okay, here we have the observation CSCS. The black currents are observation. The black curves are the observation of the electric field in the north-south component. The first panel in the central panel is the east-west component, geographically speaking, and in the last, in the bottom panel, there is the vertical component. You can see here, starting from the black curve, that we measure at about 30 and 25 a peak, a sudden variation of the electric field in all the components. If we remove the trend here is caused by the fact that the satellite is moving with a certain velocity into a plasma that is immersed into a magnetic field, causing a spurious electric field that is due by the Vikos-V effect. We can remove it, and we can see here the blue curves in which the peak is much more visible. So we were confident that potentially we are observing something that could be related to a gamma ray burst. But of course, since we are not completely sure about it, we have to model. First of all, we have to be sure that the gamma ray burst was able to produce a strong variation in the plasma density in the ionosphere. To do that, sorry, I go. We made a measurement of the total electron content. What is called total electron content. What I mean is that we can measure using GNSS or GPS satellites the total electron content in the ionosphere. And since the plasma is formed in the same part by ions and electrons, if there is an increase of electrons, we have an increase of the plasma density. And you can see here, here is the day before the occurrence of the gamma ray burst, day after the occurrence of the gamma ray burst, in the hour in which the gamma ray burst really occurred, that is between the 30 and 40. And you can see here that in Europe, we have a strong increase of the total electron content. What I mean that there is a very strong increase in the plasma density and in the ionosphere. The second fact is the timing. If there was a direct connection between the occurrence of the gamma ray burst and the occurrence of the peak in the electric field, the time should be almost the same. Here we have a direct comparison between the light curve of the gamma ray burst and the variation of the electric field. And you can see here that the peak occurs in the exactly in the zone where there are the peaks of the gamma ray burst. But here, we are not at the moment sure that this peak is directly related with the gamma ray burst. Because first of all, you can see here that there is, for example, a typical question is why there is no variation of the electric field for the first peak? Why only for the second peak? And why there is a little time delay between the second peak and the peak of the electric field? So at the moment, but I will show you here, we are not sure that this is the cause of this one. Anyway, I will, as I will show you in a couple of minutes, we developed a model which completely explains all these features in terms of all the questions that I told you here. Since we were able to explain this in our manuscript, we claimed that this is the first observation in the top side of the ionosphere of the variation of the electric field induced by gamma ray burst. Before going on, I want only to tell you that it is not the first time that we measured something in the ionosphere that is directly related with the gamma ray burst. There are many papers that I showed you here, even et al. And Val et al., that show a variation of the plasma density in the ionosphere directly related with the gamma ray burst. But they made these measurements in the bottom part of the ionosphere. In fact, they use VLF transmitter, electromagnetic transmitter from ground, and they measure how the power of the transmitter fall down, and this indicates that there is a variation in the density of the lower part of it. At the moment, before our manuscript, this was the only measurement ever done in the ionosphere, in the lower part. We made the first observation in the upper part of the ionosphere. So, are we able to quantitatively explain the electric field variation observed in the top side of the sphere? Yes, we can. And we made a model. Let's go inside the model. In order to develop a model able to represent the effect of a gamma ray burst impinging the ionosphere, we started from the ionospheric Ohm law. The physics here of the model is very simple, but as you can see later by the results, we give you a very strong and robust interpretation of the result. This is the Ohm's law. J is the current density. Sigma is the conductivity tensor, and E is the electric field. In the ionosphere, the conductivity tensor can be divided into the parallel conductivity, the outer conductivity, and the pedal conductivity that is directly related to the electric field that is parallel to the magnetic field, to the electric field that is perpendicular to the magnetic field, and to the third direction. The formation of the electric currents in the ionized layer is caused by the difference between the velocity of the ions and the electrons. In an ionosphere, the temporal variation of the electrodynamic process is low enough that we can ignore the displacement currents. So the Ampere Maxwell reduced to this one, where Mu0 is the vacuum of permeability. So by combining the ionospheric on-load and the upper maxwell equation, we are going to this very simple equation. At 500 kilometers, as you can see by this graph here, you have 500 kilometers. The only conductivity, the dominant conductivity is the sigma 0. So in our equation, we don't take into account both sigma h and sigma. In general, so our equation, since we put sigma h and sigma p equal to 0, we have that goes exactly in this form. So once in general sigma 0 is known, this equation can be numerically solved or analytically solved to obtain the electric field behavior. The equation of the parallel conductivity strongly depends on the electron density and on the electron neutral collision frequency, and of course on the mass of the electron. We can estimate using past observations and past works the electron collision frequency, okay, and we can estimate variation of the electron density using the continuity equation, in which A and L are the production coefficient and the loss coefficient. For gamma ray burst, not for gamma ray burst, sorry. In general, the recombination coefficient, as I showed you before, is directly proportional to the electron density and to the beta value, that is the loss rate. So how to model a gamma ray burst? The idea was to simulate the protection rate of a gamma ray burst using a Gaussian impulse function that has a very simple form. So our equation turned exactly into this. And so we go to integrate this one and put this relation into the electric. Finally, what we obtain for an electric field directly related to a pulse, a Gaussian pulse, and a combination rate with real measurements in the ionosphere, we obtain these curves. The difference in these curves are given by the ratio between the production rate and the loss rate. For example, if we have a production rate and the loss rate, the ratio is exactly equal to 1, we have that there is no variation of the increasing this ratio, we obtain a threshold, in this case 5, in which there is a strong pulse in the electric field. So let's make a direct comparison between observations and models. Such curves are very similar. So we can say that to obtain results similar to what has been observed on October 9, 2022, our model requires a production to loss rate ratio greater than 5. What I mean is that we can answer to the first question, why there is no variation in the electric field for the first peak of the gamma ray burst. Because for the first peak of the gamma ray burst, the ratio between alpha and beta is lower than 5. So you have that the electric field is almost unperturbed. With the arrival of the second peak of the gamma ray, the threshold is we have worked in the threshold value, and there is the variation of the electric field. So The usage of the formula interestingly related to the ratio between alpha and beta allows the model to be completely independent of the calculation of the realistic photon production rate caused by the gamma ray burst. So we can use the Gaussian index, whose evaluation, of course, needs a multi-Gauss approach and the estimation of a real topside ionospheric ion cross-section. A more accurate modeling of the gamma ray burst of the topside ionospheric electric field is in progress and will be presented in a forthcoming. So, what are the conclusions? The conclusions are that the unprecedented photon flux associated with gamma ray burst occurred on 9 of October 2022 deeply impacted the Earth ionospheric conductivity. A huge variation of the ionospheric electric field that was detected for the first time in the topside sphere is the consequence of the gamma ray burst, and we were sure about that because we modeled. In fact, the analytical model supports the observation and confirms the direct interaction between the gamma ray burst and the topside sphere, and confirms that this interaction is a threshold process. In addition, our model suggests that this threshold strictly depends on production to loss rate ratio of ions and on the time duration of the intersection process. That's all.